Greetings! For this week, you will learn about the Newton's laws of motion. Concepts will be the focus of this week's topic. Although formulas will be presented on these slides, the actual time that you are going to use them will be next week. Now, let's start by taking a brief look on who is Isaac Newton. Isaac Newton was an English physicist and mathematician and a well-known scientist. He developed the theories of laws of motion and universal gravitational law. In 1687, he published the Philosophiae Naturalis Principia Mathematica, which contains his three laws of motion. Now, let's proceed to Newton's three laws of motion. First law of motion, we have the law of inertia. Law of inertia states that a body at rest or a body in motion continues to move at a constant velocity unless acted upon by an unbalanced force. Newton's first law tells you that a moving object retains its state of motion because of inertia or the tendency of a body to resist a change in its motion. Remember, objects with greater mass have greater inertia. Formula, we have the summation of F is equal to 0 and A is equal to 0, where F is the force measured in Newton and A is the acceleration measured in meter per second squared. We have here real-life applications of the law of inertia. First, when a bus suddenly starts, the passengers sitting or standing in the bus tend to fall backward or forward. This is due to inertia of rest and can be explained as follows. When the bus suddenly starts, the lower part of the body of the passenger, which is in contact with the bus, moves along with the bus, while the upper part of the body tends to retain its state of rest due to inertia. As a result, the passenger falls backward or forward, while on the second, a rider on a running horse is thrown forward when the horse stops suddenly due to inertia of motion. Next law, the law of acceleration. Law of acceleration states that the acceleration of the body is directly proportional to the net force and inversely proportional to its mass. This basically means that the force of an object comes from its mass and its acceleration. Formula, we have F is equal to m multiplied to A, where F is equal to force measured in Newton, m is equal to mass measured in kilograms, and A is acceleration measured in meter per second squared. Real-life applications of the law of acceleration. First, it requires much more force to push a vehicle than to kick a soccer ball. Second, it requires one person to easily lift a box weighing 5 pounds, but multiple people exerting more force collectively to lift a box weighing 100 pounds. We have the third law of motion, which is the law of interaction. Law of interaction states that for every action, there is equal and opposite reaction. Now, when an object exerts a force on another object, the second object exerts an equal and opposite force back on the first object. Formula, we have F1 is equal to negative F2, where F is force measured in Newton, which means that the forces are equal in magnitude and opposite in direction. Real-life applications of the law of interaction. First, we have the action. The baseball forces the bat to the left, while the reaction, the bat forces the ball to the right. Next, action. A man jumps from the boat to the shore. Reaction, the boat slightly moves away from the shore. Let's proceed to the types of contact forces. A contact force is any force that requires contact to occur. Contact forces are ubiquitous and are responsible for most visible interactions between macroscopic collections of matter. First type of contact force, we have the normal force. Normal force is the support force exerted upon an object that is in contact with one stable object. For example, if a book is resting upon a surface, then the surface is exerting an upward force upon the book in order to support the weight of the book. Remember, normal forces are always directed perpendicular to the surface. Next type is the tension force. Tension force is the force that is transmitted through a string, rope, cable, or wire when it is pulled tight by forces acting from the opposite ends. The tension force is directed along the length of the wire and pulls equally on the objects on the opposite ends of the wire. We have here a graphics interchange format that shows the difference between compression and tension. Next, we have the types of friction. Now, when we say friction, it is a force that acts opposed the relative motion of two surfaces. First, we have the static friction. The force of static friction keeps a stationary object at rest. Therefore, to initiate the motion of the box, the beam must overcome the force of static friction. Formula under static friction. We have static force or static friction is equal to the normal force multiplied to the coefficient of static friction, where static force is measured in Newton. Normal force is also measured in Newton, while coefficient of static friction remains to be unitless. Next type of friction, we have the kinetic friction. Kinetic friction is a force that acts between moving surfaces. Formula: kinetic force or kinetic friction is equal to the normal force multiplied to the coefficient of kinetic friction, where kinetic force is measured in Newton. Normal force is also measured in Newton, while coefficient of kinetic friction remains to be unitless. Next is a table of coefficients of static and kinetic friction given a certain material. Let's now have the fluid resistance. Fluid resistance refers to the forces a fluid places on a moving object in the opposite direction to the movement, also known as drag. Drag is the force created by fluid to resist the motion of an object moving through it. Different examples under fluid resistance. One form of fluid friction is when a fluid is moving over the surface of a solid object. For example, water moving along the ground is held back slightly due to fluid friction. The pressure from the fluid times a unit area equals the normal force between the fluid and the solid. Next example, solid object moving over a fluid. When an object is moving along the surface of a fluid, there is a friction resistance holding back the motion. Most objects will sink somewhat in the fluid such that the object is flowing through the fluid. This can be seen when a boat sinks across the water. There is both fluid friction on the bottom and resistance as it flows through the water. Lastly, object moving inside fluid. When a solid object is moving inside the fluid, such as water or air, there is a fluid resistance as the object tries to flow through the fluid. This resistance is a combination of resistance due to the shape of the object and surface fluid friction. Examples include air resistance on an airplane and water resistance on a submarine. There is also some water resistance effect on a boat moving along the surface of some body of water. Next is a free body diagram. Free body diagram is a graphical illustration used to visualize the applied forces, moments, and resulting reaction on a body. This is what you usually see in a free body diagrams. Lastly, free body diagram example with an angle.